If you were to take a highly sensitive thermometer, right, and travel in some hypothetical spaceship far, far beyond the edges of our Milky Way.
Oh, way out into the deep void.
Yeah, exactly. Just stick that thermometer into the absolute deepest, emptiest vacuum of intergalactic space.
Yeah,
You'd probably expect it to read absolute zero.
most people would, yeah.
But it wouldn't. That is honestly one of the most profound realizations of 20th century astronomy. The thermometer would read roughly 2.7 degrees above absolute zero.
Which is incredibly specific.
Right. Because the entire universe, everywhere we look, is just quietly humming with this microscopic leftover heat of the Big Bang itself. Welcome back to the Bureau of the Unexplained, where we dive into all things weird and unexplained.
It's fantastic to be back in the investigative chair today. Because while that 2.7-degree hum is a total triumph of modern physics, it's also the backdrop for something deeply, deeply unsettling.
Unsettling is honestly the perfect word for it, because we look up at the night sky, or rather, I guess cosmologists look at their data, and they expect the universe on its grandest scales to, follow the rules.
Yeah, the foundational rules. It's
Yeah.
supposed to be smooth, orderly,
Yeah.
uniform.
Exactly. But today, for this deep dive, we are investigating a patch of the sky where that foundational rule simply breaks. We are looking at an anomaly so vast and so peculiar that it basically threatens to upend our entire understanding of reality.
We're talking about the cosmic microwave background cold spot.
The CMB cold spot.
Right. And to cosmologists, it is the ultimate cold case. I mean, it's a mystery that has survived over 2 decades of the most intense scientific scrutiny humanity can possibly muster.
And it sounds so unassuming, right? The cold spot.
Yeah.
It's a cold spot. But I want you, the person listening right now, to treat this deep dive as a cosmic detective story. Because we have a massive stack of evidence to get through today.
Like, we really do.
We are pulling data from the Dark Energy Survey, analyzing maps from the Planck and WMAP satellites, looking at the cutting-edge, newly released imagery from the Euclid Space Telescope.
Which is just phenomenal data, by the way.
It really is. And we're even diving into some incredibly dense theoretical physics papers on string theory and the multiverse. So we have our crime scene, which is the entire observable universe.
That's a big crime scene.
Yeah, just a bit. And we have our victim, which is the uniform temperature of the early cosmos. And we have an anomaly that literally refuses to be explained away. So to really understand the gravity of this, we need to open the case file and travel back in time, roughly 13.8 billion years.
Right, because to understand the anomaly, we have to deeply understand the background radiation it actually sits within. The cosmic microwave background, which we will just refer to as the CMB to save time.
Good call.
It is the oldest light we can possibly see.
Right, because before a certain point in time, there literally wasn't any light that could travel through space, was there?
No, not at all. That's the key to all of this. In the immediate aftermath of the Big Bang, the universe was unfathomably hot and incredibly dense. I mean, it was a plasma soup of fundamental particles.
It's just chaotic mess.
Exactly. If a photon, a particle of light, tried to move, it would immediately smash into a free-roaming electron or a proton. It was like trying to drive a car through a densely packed crowd of people. You just bounce off the nearest person. The universe was completely opaque. Glowing, sure, but opaque.
So we couldn't take a picture of that era, even if we had a telescope big enough, because the light literally couldn't escape the crowd to reach the camera.
Precisely. But the universe was expanding, and as it expanded, it cooled down. About 380,000 years after that initial expansion, a monumental shift occurred. The temperature dropped just enough to about 3,000 Kelvin for those free-roaming electrons to slow down.
And they got captured by the protons, right?
Right. They were captured, and they formed the very first neutral hydrogen atoms.
I've seen this referred to in the literature as the epoch of recombination.
Yeah, which is a slightly confusing historical term, honestly, since they were combining for the very first time, not recombining, but yes, that's the term. And the critical outcome of this epoch was that the crowd suddenly cleared out.
The electrons got locked up.
Exactly. They were locked into atomic orbits, so the universe instantaneously became transparent. That trapped light was suddenly free to travel in every direction across the cosmos.
And that light is still traveling today, which is wild to think about. It has been flying through space for 13.8 billion years, finally hitting the detectors on our satellites.
Yeah, it's ancient light.
But because the universe has been stretching out that whole time, the light has been stretched too, hasn't it? The wavelength has elongated, cooling down from that initial 3,000 Kelvin heat to just like microwave radiation today, just a few degrees above absolute zero.
That is the foundation of our standard model of cosmology. It's often called the lambda cold dark matter model, or just lambda CDM. And when we map this CMB across the entire sky, we find that it is remarkably uniform. It is isotropic. But crucially, it is not perfectly smooth.
Because if it were perfectly smooth, nothing would exist, right?
Yeah.
I mean, every single millimeter of the early universe had the exact same density and temperature. Gravity would have pulled on everything equally in all directions.
Exactly. It would be a perfectly balanced tug of war.
Yeah, so nothing would have clumped together. No galaxies, no stars, no planets. We definitely wouldn't be sitting in the studio having this conversation.
Right. The simple fact that we exist means there had to be imperfections. And lambda CDM predicts these. It states that incredibly microscopic quantum fluctuations in the very first fraction of a second of the universe were blown up to macroscopic scales during an event called inflation.
And those are the spots we see on the map.
Yes. These density fluctuations left behind tiny temperature variations in the CMB. Slightly denser regions of dark matter pulled in more regular matter, becoming slightly hotter. Emptier regions became slightly colder.
So when you say tiny temperature variations, what kind of scale are we talking about here? If you're listening to this in your car or at the gym right now, just imagine trying to measure this. How small is a typical fluctuation?
We are measuring in micro-kelvins, millionths of a degree. It's almost incomprehensibly subtle.
Wow.
And the standard model predicts that these fluctuations should follow a standard Gaussian distribution. Think of it like rolling millions of dice. You expect a certain predictable bell curve of outcomes.
So mostly average rolls with a few high and low outliers, but all within a specific range.
Right. In the CMB, you expect the random variations to mostly hover around 18 microkelvins warmer or cooler than that average 2.725 Kelvin background. Furthermore, the physics of how sound waves move through that early plasma soup dictates the size of these spots. The largest of these typical temperature spots should only cover an angular scale of about 1 degree across the sky.
Okay, so that gives us our baseline for the crime scene. We expect random static, a bell curve of tiny 1-degree blips hovering around 18 microkelvins. That is the normal, expected behavior of the universe.
Yes, that's what the math says we should see.
But then somebody develops the film on this cosmic baby picture, and they find something that completely shatters the bell curve.
They absolutely did. The first real glimpse of the anomaly came in 2004, courtesy of NASA's Wilkinson Microwave Anisotropy Probe. We call it WMAP.
WMAP, yeah.
The scientific community was mapping the southern celestial hemisphere down toward the constellation Eridanus when they spotted a massive temperature depression.
Okay, so if a normal fluctuation is around 18 microkelvins, how deep does this drop go?
It plunges anywhere from 70 to a staggering 150 microkelvins colder than the surrounding average.
Wait, 150? That is an astronomical drop compared to the background noise.
It really is. The depth is shocking, but the geometry is what truly caused headaches for the astrophysicists. Because this is not a normal 1-degree fluctuation, the cold spot spans a massive 5-degree radius across the sky.
5 degrees, that's huge.
It's massive, and it has a distinct morphology. It is not just a random blob. It has a central, deeply cold core, which is surrounded by an anomalously warm ring. It completely defies the visual language of the surrounding random static.
Let me try to put an analogy to this, just because staring at CMB maps can feel a bit abstract for anyone who hasn't seen one.
Sure, go for it.
Imagine you're looking at the screen of an old, untuned analog television set. It's just that chaotic, flickering snow. Black, white, and gray dots everywhere. There's your standard Gaussian distribution, right?
Yeah.
It's random, and it's uniform in its randomness.
Yep, a perfect visual for Gaussian noise.
But then you look down at the lower left quadrant of the screen, and amidst all that flickering static, there's a perfect, dark, unmoving thumbprint.
I like that.
And around the dark ridges of the print, there's a bright white halo. It doesn't look like static at all. It looks like an entirely different phenomenon superimposed on the screen.
That is a phenomenal way to visualize it. And that thumbprint is a statistical nightmare for cosmologists.
Because it shouldn't be there.
Exactly. When researchers run tens of thousands of computer simulations of the universe, strictly adhering to the lambda CDM model and its Gaussian rules, a spot this cold, this large, and with this specific ringed morphology almost never appears.
So what are the actual odds?
Well, the probability of the cold spot forming purely by random chance is heavily debated in the literature, but the consensus places it somewhere between 1 in 50 and 1 in 2,000.
1 in 2,000. So we are looking at something incredibly improbable. It feels like a direct violation of that cosmological principle you mentioned earlier. The idea that the universe should look generally the same in all directions.
It certainly challenges the assumption of large-scale isotropy, yes, but any rigorous scientist looking at a 1 in 2,000 anomaly has to start with the most boring, mundane explanation possible.
Right, of course. If I see the dark thumbprint on my TV screen, I don't immediately assume the broadcast is picking up signals from a ghost dimension.
Obviously not.
My first assumption is that my screen is dirty. So could this entire mystery just be a smudge on the camera lens? Like, could it be a systemic error in the WMAP satellite's instruments?
That was the immediate prevailing theory among skeptics. The detectors on WMAP were incredibly sensitive, and mitigating instrumental noise or galactic foreground interference is notoriously difficult. So it was a very valid question.
But I'm guessing it didn't hold up.
It did not. That theory was definitively dismantled in 2013. The European Space Agency launched the Planck satellite, which was generations ahead of WMAP. I mean, it utilized entirely different instrumentation, sweeping the sky at different frequency bands with significantly higher resolution.
And when Planck looked at the constellation Eridanus,
It observed the exact same cold spot, with the exact same 5-degree radius, the same hot ring, and the same statistical significance. Planck confirmed that we were not looking at a WMAP glitch. Yeah, the smudge wasn't on the lens. The thumbprint is a physical reality baked into the fabric of the cosmos.
which genuinely turns this into an eerie investigation, especially when you read into the broader context of the CMB maps. The cold spot isn't just a solitary freak occurrence, is it? It seems to be part of a larger, incredibly unsettling pattern that cosmologists have somewhat nervously nicknamed the axis of evil.
Yeah, the term is definitely dramatic, but the underlying data warrants the unease. When scientists analyze the largest scale temperature fluctuations across the entire sky, these are called the dipole and quadrupole moments, they find mysterious alignments.
Alignments that shouldn't exist.
Right. Instead of being randomly distributed as standard inflation would predict, several of these massive features, including the general region of the cold spot, seem to align along a specific axis.
It's like the universe has an equator or something.
It hints at a preferred direction in space, a hidden architecture or orientation to the universe that absolutely should not exist under standard physics.
Okay, so if it's not a dirty telescope lens and the anomaly is real, we need to figure out what cast that shadow. We need suspects for our case file.
Bring them in.
Well, if we're looking at a photon that has been traveling for 13.8 billion years, there's an unimaginable amount of physical space between the origin of that light and our telescopes here on Earth. Maybe the light started out completely normal, but something happened to it on the way here.
That is the exact logical pivot the scientific community made. They moved away from analyzing the background radiation itself and started analyzing the intervening physical space. They began searching for something massive enough to siphon energy away from light itself.
And that search led directly to suspect number one, an astronomical leviathan, the Eridanus Supervoid.
A supervoid.
It sounds like something out of a science fiction horror movie. To understand how a giant empty space could possibly cool down a photon, we need to unpack the mechanics of this. We're talking about something called the Integrated Sachs-Wolfe effect, or the ISW, correct?
Yes. The ISW effect is a brilliant piece of relativistic physics. To grasp it, you have to remember that the space between galaxies is not flat and static. The universe is a complex, evolving landscape of gravitational potentials.
Okay, map that out for me.
Sure. There are massive superclusters of galaxies, which act like deep gravitational wells, and there are vast, relatively empty regions called voids, which act like gravitational hills.
Wait, a void is a hill. That feels a bit counterintuitive. I mean, if a dense cluster is a well that pulls you in, I guess an empty space would be the opposite, but a hill.
Exactly. Imagine a photon from the CMB flying toward Earth. It has to navigate this terrain. When the photon approaches a dense supercluster, it falls into that gravitational well. It gains energy, becoming slightly hotter or blue-shifted.
Like rolling down into a valley.
Right. And as it climbs out the other side, it expends that exact same amount of energy, becoming red-shifted back to its original state.
So it breaks even. No net change.
In a static universe, yes. Now let's reverse the terrain. When our photon encounters a supervoid, a massive region with significantly less matter than average, it basically has to climb a gravitational hill. The surrounding, denser regions of the universe are pulling back on it.
Because there's no mass inside the void to pull it forward.
Exactly. The photon expends energy to climb this hill. Its wavelength stretches out and it becomes colder.
But shouldn't the break-even rule still apply here? Once it reaches the top of the void and starts exiting down the other side towards us, shouldn't it get pushed along by the gravity of the denser regions ahead of it, regaining that exact same energy?
If the universe were solely dominated by matter, you would be absolutely right. The photon would roll down the hill, regain its energy, and there would be no net change in the CMB temperature. But we do not live in a purely matter-dominated universe.
No, we do not.
We live in a universe dominated by dark energy.
The mysterious, invisible force that is actively accelerating the expansion of the universe.
That acceleration is the crucial mechanism, because dark energy is causing space itself to expand at an accelerating rate. The gravitational structures within that space are revolving while the photon is in transit.
Okay, I think I see where this is going.
When a photon enters a massive supervoid, it starts climbing the hill. But these voids are so unimaginably huge that it takes millions of years for the photon to cross it. And during those millions of years, dark energy is actively stretching the void out, making it physically wider and gravitationally shallower.
Let me try to put an analogy to this. It's like a bicyclist rolling down into a very deep valley.
Okay, let's hear it.
Normally, you build up a ton of speed going down, and you use that exact momentum to coast right back up the opposite side. You exit at the exact same speed you entered.
Right.
But imagine that while the bicyclist is at the very bottom of the valley, some massive earthquake literally stretches the valley floor, pulling the far wall further away and making the incline much shallower.
Oh, that's good.
The momentum you built up on the way down is no longer enough to get you out. You have to pedal harder. You have to expend your own energy to climb out.
That analogy captures the mechanics perfectly. The photon enters a steep gravitational potential, but it exits a shallower one. Because the hill flattened out while the photon was traversing it, the photon never regains the full amount of energy it spent climbing in.
It suffers a permanent energy loss.
It does. So by the time that photon finally reaches the Planck satellite, it registers as significantly colder than the surrounding light. That is the integrated Sachs-Wolfe effect in a dark energy-dominated universe.
So the theory is brilliant. We have a clear, physically sound mechanism for how you can drain energy from light and create a gold spot. The next obvious question is, does the suspect actually exist? Do we see a giant expanding void exactly where the cold spot is?
We do. Around 2015, astronomers used data from Hawaii's Pan-STARRS 1 telescope and the WISE satellite to survey the distribution of galaxies in the direction of the constellation Eridanus. And they found an absence of galaxies so large it practically defies comprehension.
The Eridanus Supervoid.
They discovered the Eridanus Supervoid.
How big is a supervoid, actually? I mean, we throw that word around, but what is the scale here?
Well, the Eridanus Supervoid is located about 3 billion light years away from us, which puts it relatively close in the grand timeline of the cosmos. As for its size, it spans a staggering 1.8 billion light years across.
My brain physically cannot visualize 1.8 billion light years of nothing.
Yeah.
I can't do it.
It's arguably one of the largest single structures, or rather lack of structures, ever identified by humanity. Inside this colossal volume of space, the density of matter is roughly 30% lower than the average density of the surrounding universe.
Okay, so we found the suspect holding the weapon, standing over the victim. We have a massive 1.8 billion light-year void located in the exact same line of sight as the CMB anomaly, and we have the ISW effect explaining exactly how it could steal the photon's energy. This feels like case closed.
It really does.
The giant void caused the giant cold spot.
That was the triumphant headline for about a year. But in astrophysics, having a suspect just isn't enough. The math has to balance flawlessly. The gravitational ledger must be balanced. And this is where the Eridanus Supervoid's alibi began to completely unravel.
Wait, what went wrong? The void is there, isn't it?
The void is there, but the issue is depth. To truly calculate the ISW effect, you can't just count the missing visible galaxies. Visible matter is just the foam on the cosmic ocean. The bulk of the gravitational pull, or lack thereof, is dictated by invisible dark matter.
Right, because dark matter makes up most of the mass.
Exactly. So to prove the void was deep enough to cause the cold spot, cosmologists needed a three-dimensional map of something they literally couldn't see. Enter the Dark Energy Survey, or the DES.
I know the Dark Energy Survey is a massive collaboration. How exactly do you map invisible mass? That sounds impossible.
It requires extreme precision. The EES consortium built a specialized 570 megapixel digital camera known as DCAM. They mounted this behemoth onto the 4-meter Blanco telescope, situated high up in the Chilean Andes, far above most atmospheric interference.
Okay, so they have a great view.
The best. Over several years, they meticulously stared at the Eridanus region, employing a technique called weak gravitational lensing.
Now, I'm familiar with strong gravitational lensing. That's when a massive galaxy cluster literally bends the light of a background galaxy into giant glowing arcs or rings. It acts like a cosmic magnifying glass. But what is weak lensing?
Strong lensing is obvious and dramatic. Weak lensing is incredibly subtle. It relies on looking at the shapes of millions of distant background galaxies. Now, we don't know the original true shape of any individual background galaxy, but statistically, if you look at a large enough sample, their orientation should be completely random.
Like dropping a handful of toothpicks on the floor. They point in every direction.
Exactly. But if there is a massive structure of dark matter sitting between us and those background galaxies, the dark matter's gravity will subtly warp the space around it. The light passing through that space gets slightly bent.
So it alters the image.
Yes. So when we look at our field of toothpicks, we notice that they aren't completely random anymore. There is a tiny systematic stretching or alignment in their shapes. By measuring this microscopic shear across millions of galaxies, astrophysicists can reverse engineer the mass of the invisible dark matter foreground that caused the distortion.
That is just brilliant. It's like looking at the distorted pebbles at the bottom of a rushing river and using those distortions to map out the invisible currents of the water flowing above them.
It is one of our most powerful cosmological tools. So the DES team spent years compiling this weak lensing data for the Eridanus region to reconstruct a true 3D mass map of the supervoid. And their findings were a devastating blow to the ISW theory.
The void wasn't big enough.
The void was confirmed to exist, yes. But the lensing signal, the actual measured gravitational depth of the void, was roughly 30% lower than what theoretical models suggested it should be.
I'm making sure I follow. The void is physically wide, 1.8 billion light years across.
Yeah.
But gravitationally, it's too shallow.
Exactly. It simply lacks the gravitational teeth required to steal that much energy from a passing photon. When the DES team ran the hard math, combining the newly mapped depth with the physical size of the Eridanus Supervoid, they found that it could only generate a temperature drop of about 10, maybe 20 micro-kelvins.
But the CMB cold spot drops by up to 150 micro-kelvins.
Precisely. At its absolute maximum theoretical limit, the Eridanus Supervoid can only account for maybe 10 to 20% of the anomaly.
That's nothing.
Right. The void is definitely guilty of creating a minor temperature dip, a cosmic misdemeanor, if you will, but it is absolutely incapable of committing the 150 microkelvin felony we are investigating.
That is wild.
Yeah.
The biggest, emptiest space humanity has practically ever observed is basically just a bystander in this mystery.
And it gets worse for the void advocates. The final nail in the coffin came from analyzing control fields. In rigorous science, you need a control group, right?
Always.
Researchers pointed their instruments at a completely different region of the southern sky, a sector known as the gamma G23 field.
And what is special about gamma G23?
It is remarkably similar to the Eridanus region. It features a similar overall distribution of galaxies, and crucially, it contains its own massive supervoids of comparable scale. But when the researchers cross-referenced the optical data of the gamma G23 voids with the Planck satellite's temperature maps of that exact same patch of sky, there was nothing.
Wait, nothing?
No corresponding cold spot whatsoever.
Wow. So that breaks the causal link entirely.
Yeah.
You cannot claim that giant voids inherently cause massive CMB temperature drops if you have an identical giant void sitting over in gamma G23 doing absolutely nothing to the background radiation.
Exactly. The fact that the Eridanus supervoid aligns perfectly with the CMB cold spot appears to be nothing more than a wildly improbable coincidence of line-of-sight geometry. The void is innocent.
Okay, so if standard cosmological mechanics, dark energy stretching massive empty spaces cannot explain this thumbprint, we are forced to look at alternatives. We have to venture into the weirder, non-standard suspects. Where did the astrophysics community pivot to next?
Well, with the grand, large-scale void theory collapsing, some researchers decided to look much, much closer to home. Instead of a massive absence of matter billions of light years deep, what if the culprit was a messy abundance of matter right in our cosmic front yard? This brings us to the smokescreen theory, primarily focusing on something called galaxy stripping.
Galaxy stripping. That sounds incredibly violent. What exactly is getting stripped?
It is incredibly violent on a galactic scale. In March of 2024, a team of researchers shifted their focus from the deep void to the foreground. Sitting almost directly in front of the absolute coldest, deepest part of the CMB anomaly is a massive, gravitationally bound cluster known as the Eridanus Supergroup. This group contains massive galaxies, notably NGC 1407 and NGC 1332.
Okay, so we have a cluster of galaxies sitting between us and the coldest part of the spot. But galaxies are bright and hot. How does that make things look colder?
By acting as a literal smokescreen. When giant galaxies exist in a tight group, they are constantly interacting gravitationally. As they pass near each other, their immense gravitational tides rip at one another. The researchers analyzing the Eridanus supergroup found that these specific galaxies are severely hydrogen deficient.
Oh, I see.
Yeah, they are exhibiting massive tidal stripping of atomic hydrogen gas.
So they're bleeding gas out into the intercluster space. They're surrounded by a massive turbulent cloud of their own torn-apart atmosphere.
Exactly. And the theory proposes that this vast, cold cloud of stripped atomic gas could be interacting with the ancient CMB photons. It might be scattering, absorbing, or altering the microwave radiation in a localized way that mimics a massive cosmic temperature drop.
That's fascinating.
In their paper, when the researchers modeled this specific foreground interference and mathematically subtracted it from the CMB data, the statistical significance of the cold spot dropped considerably.
Wait a minute, so you're telling me this entire decades-long mystery, this anomaly that had us questioning the fundamental isotropy of the universe, might just be cosmic dust on our windshield. The smudges on the satellite lens is just a cloud of gas floating right in front of our line of sight.
That's the theory. It's a highly localized, physically motivated explanation. It is certainly much more mundane than invoking new physics or exotic energy.
But I have to push back on this. My brain is snagging on the geometry.
I don't blame you.
We established earlier that the cold spot isn't just a blob. It spans a massive 5-degree radius. It has a deeply cold core, surrounded by a distinct, hot, ring-like structure. If I look at a turbulent, messy, violently torn-apart cloud of galaxy gas, does that naturally form a perfect 5-degree circle with a hot halo?
You are hitting on the exact fatal flaw of the smokescreen theory.
I knew it.
The geometry is completely wrong. While local gas stripping can absolutely cause localized temperature variations and obscure background signals, the process is incredibly messy and chaotic. It does not naturally produce the geometric precision, the specific non-Gaussian morphological profile, or the sheer vast angular scale of the cold spot.
Too neat.
Way too neat. The galaxy group is a localized knot. The cold spot is a massive structured projection. Trying to fit the galaxy stripping data to the cold spot is like trying to explain a perfectly round, rimmed crater by pointing to a random pile of scattered rocks. The scale and the shape just don't fit.
Okay, so the mundane foreground smokescreen doesn't hold up to scrutiny. If we can't solve this with empty voids and we can't solve it with dirty gas clouds, we're basically running out of standard physics. What is the exotic alternative? You mentioned earlier something called cosmic textures. Now, I'll be honest, when I read the word texture in an astrophysics paper, it feels like we're just inventing invisible monsters to explain a shadow on the wall.
Invisible monsters is actually not a terrible way to conceptualize early universe topological defects. They are hypothetical, extreme, and completely invisible to our standard senses.
Okay, let's unpack this carefully. What exactly is a cosmic texture, and how does it form?
To understand textures, we have to journey back to a fraction of a second after the Big Bang. At this moment, the universe was unfathomably hot. And because it was so hot, the fundamental forces of nature, electromagnetism, the strong nuclear force, and the weak nuclear force, were all unified into a single symmetrical superforce.
Right, but as the universe expanded, it rapidly cooled down.
And as it cooled, it underwent violent phase transitions. The superforce shattered. The forces separated from one another, breaking the initial symmetry of the universe. The best way to visualize this phase transition is to think about liquid water freezing into solid ice.
Okay, water to ice. I can visualize that.
When a calm pond freezes, it doesn't freeze into one single, perfectly unified, flawless crystal of ice. Different patches of water freeze at slightly different moments, with their crystalline structures orienting in different directions. And when these different misaligned patches of ice grow and bump into each other, they don't merge perfectly.
The crack.
They form physical cracks, fault lines, or trapped bubbles where the structure of the ice is defective.
Like the white, cloudy lines you see in the middle of an ice cube.
Exactly. Now, apply that concept to the fabric of space-time itself. During these early universe phase transitions, specifically at unimaginably high energy scales, around 10 to the 16th gigaelectron volts, different regions of the expanding vacuum of space may have frozen into different energy
This
states.
is wild.
When these mismatched regions met, they formed macroscopic cracks in the universe. These are known as topological defects.
So the universe itself cracked.
Yes, a cosmic texture is a specific type of three-dimensional topological defect. You can think of them as incredibly dense, knotted balls of pure vacuum energy left over from the symmetry breaking of the early universe.
Okay, I have a knot of pure energy. How does that create a perfectly round cold spot 13 billion years later?
Because these textures are inherently unstable. As the universe continues to expand, it stretches the texture, the knot gets pulled tighter and tighter until the tension becomes too great, and the entire structure violently unwinds and collapses in on itself at the speed of light.
That sounds cataclysmic.
Is an event of extreme gravitational violence. The rapid evolution and sudden collapse of this massive gravitational potential creates a highly localized, intense warping of spacetime. If ancient photons from the CMB happen to pass through this specific region at the exact moment the texture is collapsing, they experience a dramatic, highly specific shift in energy.
Oh, I see the connection now.
What is fascinating is that theoretical models and supercomputer simulations have shown that the collapse of a single cosmic texture could theoretically match the temperature profile of the cold spot flawlessly.
Wait, really? It actually creates the hot ring and the cold core?
With striking precision, the mathematics of a collapsing texture naturally generate a spherically symmetric gravitational wave that would leave a distinct cold core and a warm surrounding ring on the CMB.
Then why are we still having this deep dive? I mean, if the math matches the profile flawlessly, why aren't astrophysicists popping champagne and declaring victory for the cosmic textures?
Because of the prerequisite assumptions. To claim a cosmic texture caused the anomaly is to require a highly specific, entirely unproven branch of high-energy particle physics.
We haven't actually found one.
We have never observed a topological defect. We have no concrete evidence that the grand unified phase transitions of the early universe occurred in the exact way required to produce them. It replaces one observable mystery, the cold spot, with an even larger, entirely untestable theoretical assumption. It is mathematically beautiful, but scientifically unverified.
I see. So the Eridanus void is too shallow, the galaxy stripping is too messy and ignores the geometry, and the cosmic texture theory requires us to blindly accept a new realm of particle physics that we can't actually prove exists.
You have perfectly summarized the frustration of the entire cosmological community. Standard physics has failed to lock up a conviction, exotic topological defects are too speculative, and that failure forces us to look at the absolute edge of the theoretical board. We must consider the most radical paradigm-shifting theory currently circulating in astrophysics.
My brain is warmed up. What is suspect number 3?
Suspect number 3 proposes that the cold spot isn't a shadow cast by an empty void. It isn't dust on the windshield. And it isn't an invisible knot of energy. It is a physical bruise. A lingering scar left behind when our universe violently collided with another universe.
When worlds collide, you're talking about actual physical evidence of the multiverse.
I am. Specifically, we are diving into the framework of eternal inflation and the string theory landscape.
Okay, I need to take this step by step. Let's start with inflation. I understand the standard model of inflation. The idea that a fraction of a second after the Big Bang, the universe expanded exponentially, stretching out quantum fluctuations to make the large-scale structure of the universe we see today. It expanded insanely fast, and then it stopped, settling into the slower expansion we experience now.
That is standard inflation, and it solves many cosmological problems. But eternal inflation takes that mathematical concept and extends it to its logical, terrifying extreme. Eternal inflation suggests that this rapid, exponential expansion never actually stopped everywhere.
Wait, what do you mean?
Instead, the fundamental background of reality, a state of space-time physicists refer to as a false vacuum, is eternally, constantly expanding at an exponential rate.
If it's eternally expanding everywhere, how are we sitting here right now in a stable universe?
Because within this violently inflating false vacuum, microscopic quantum fluctuations can cause tiny, localized pockets of space to stabilize. They drop out of the chaotic false vacuum into a lower, stable energy state called a true vacuum. When a pocket drops into a true vacuum, it stops inflating wildly. It forms a boundary. It forms a bubble.
A bubble, like water boiling in a pot.
It is the absolute best analogy for this complex math. The universe's native high-energy state is the boiling water. The bubbles of steam constantly popping into existence within the water are the pocket universes. Our entire observable universe, every galaxy, every quasar, every star we can see is contained entirely within the inside of just one of those microscopic bubbles.
This is deeply humbling. Okay, we are inside a bubble, but if the water is boiling and there are other bubbles of true vacuum popping into existence around us in the false vacuum,
Then they can interact. In this eternal inflation model, governed by complex mathematics known as the Coleman-de Lucia mechanism, these bubble universes are constantly nucleating and physically expanding outward. And the math explicitly allows for the probability that two expanding bubbles could nucleate close enough to each other that their expanding boundaries eventually crash.
they bump into each other. It is a literal cosmic fender bender.
Yes. A fender bender between two entirely distinct realities occurring during the unimaginably violent earliest moments of our universe's inflationary epoch.
And the hypothesis is that the cold spot is the physical dent left in our bumper.
That is precisely the theory. When our bubble universe collided with a neighboring bubble, the collision violently disrupted something called the inflaton field. This is the underlying scalar field that was actively driving our universe's expansion. A disruption of this magnitude in the inflaton field would permanently alter the density and temperature of that specific region of space.
But wait, hold on. If two entire universes collide, wouldn't that just destroy everything? Why didn't our bubble just pop? Why is the only evidence a slightly colder patch of microwave static?
It all depends on the intricate dynamics of the domain wall, the physical boundary between the two different vacuas. The physics dictate that the bubbles wouldn't necessarily destroy each other. They would essentially fuse at the point of impact, creating a distinct boundary layer.
Okay, that makes sense.
But the most compelling piece of evidence supporting this multiverse theory isn't just the temperature drop, it is the geometry. Recall the specific shape of the cold spot.
The massive 5-degree circular disk, the thumbprint.
Exactly. Now, I want you to visualize this. If two expanding soap bubbles floating in the air happen to merge together, what shape does the shared wall between them take?
The intersection between two round spheres is a perfectly flat circular disk.
Exactly. Now we have to scale that geometry up to cosmology. Mathematically, our universe is a four-dimensional hypersphere expanding through space-time. When two four-dimensional hyperspheres intersect, they create a three-dimensional boundary. And when that three-dimensional boundary is projected down onto the two-dimensional map of our cosmic microwave background,
It projects as a mathematically perfect 2D disk.
precisely. The complex mathematics of a multiverse collision naturally and elegantly dictate the exact perfect circular geometry that we actually observe in the anomaly.
Okay, my brain is officially melting, but I am following you. The math of the shapes lines up perfectly.
It goes even deeper into the physics. The collision intrinsically breaks the fundamental symmetry of our bubble universe. A single, solitary, undisturbed bubble universe possesses a specific mathematical symmetry classified as SO31.
That's
The symmetry group is governed by 6 specific generators, and in plain terms, it is the mathematical reason why the universe appears uniform and isotropic in all directions.
Okay, so SO31 means everything looks the same everywhere.
Right. But when a collision occurs, that inherent symmetry is violently broken down to a lesser symmetry group known as SO21, which only has 3 generators.
And what does losing those generators mean for the physical space of the universe?
It means that instead of being completely uniform, the universe suddenly has an axis, a preferred direction, and that axis points exactly radially toward the center of the colliding bubble. This mathematical fingerprint, the breaking of SO31 to SO21, dictates the exact temperature gradient of the resulting bruise.
Wow.
Theoretical physicists who modeled this collision formulated a highly specific equation for the temperature drop. The equation relies on a dimensionless coefficient lambda, the co-moving distance d, and the coordinate distance x.
Let me guess. That equation doesn't just create a random cold spot.
No, the equation strictly dictates that the temperature profile will follow a specific cosine pattern, radiating outward from the absolute center of the collision axis.
A cosine pattern, meaning it drops deeply into a cold core, rises back up to a warm ring, and then normalizes. It perfectly mathematically predicts the Eridanus anomaly's exact morphology.
It matches it beautifully. It organically explains why the cold spot is a single, large, coherent, geometrically perfect feature, rather than a messy collection of random peaks and valleys like the galaxy stripping theory would produce.
This is the most breathtaking scientific story I have ever heard. But here is the massive, unavoidable problem. It's just a story, isn't it? It's
Yeah.
beautiful, elegant math on a whiteboard. But how do you actually physically prove that our universe was rear-ended by another dimension 13.8 billion years ago? We can't exactly swab the cold spot for the other universe's DNA. We can't swap cosmic insurance information. How do we test this?
That is the ultimate gauntlet for theoretical cosmologists, dragging a mathematically elegant multiverse theory out of the realm of philosophy and into the realm of observable, empirical, testable science. To prove a collision happened, astronomers are not looking at temperatures anymore. They are desperately searching the CMB for a highly specific, smoking gun clue: polarization signatures.
Polarization. I understand the basic concept, like polarized sunglasses blocking glare by only letting light waves oscillating in a certain direction pass through. But how is the ancient light of the universe polarized?
When those ancient CMB photons finally escaped the plasma soup 380,000 years after the Big Bang, they didn't just fly straight, they scattered off the last remaining free-roaming electrons. That final scattering event actually polarized the light, imparting a specific orientation to its waves.
Okay, so our telescopes can measure not just the temperature of the light, but the exact physical orientation of the light waves.
Yes. And a violent collision with another universe wouldn't just leave a temperature dent in that patch of sky. The sheer trauma of the symmetry-breaking event would twist and distort the polarization of the light in a highly predictable, distinct way. We are hunting for two specific polarization signatures. First, we're looking for a purely symmetric E-mode polarization field.
What exactly is an E-mode?
E-mode stands for electric mode. It is a gradient-like polarization. Standard, random quantum fluctuations from normal inflation create messy, random E-modes all over the sky. But a multiverse collision would create a highly organized, perfectly axisymmetric E-mode pattern, ringing precisely around the center of the cold spot. It would look like a bullseye of twisted light.
A bullseye of E-modes. That is the first signature. That's the second.
The second is even more elusive and arguably more definitive. A collision of that unimaginable magnitude wouldn't just twist light. It would violently disturb the underlying fabric of space-time itself, generating a massive localized burst of gravitational waves. These gravitational waves would imprint a fundamentally different kind of twist on the light, called B-mode polarization.
B-modes. I know scientists have been searching for B-modes across the whole sky to prove the standard model of inflation.
They have, but the B-modes caused by a multiverse collision wouldn't be spread across the whole sky. They would be entirely localized, trapped within the boundary of the collision disk. The researchers who modeled this described the expected B-mode signature as looking like a Jackson Pollock painting of splattered, chaotic, twisting energy confined purely to the specific coordinates of the cold spot.
A localized Jackson Pollock painting made of gravitational waves. That is an incredibly specific, observable prediction. So the obvious question is, have we looked for it? Did we point our best satellites at the cold spot and search for the bullseye and the splattered paint?
We have absolutely looked. A brilliant team led by cosmologists Stephen Feeney and Hiranya Paris undertook this exact challenge. They utilize an incredibly advanced statistical technique known as Bayesian evidence analysis to meticulously scan the WMAP and Planck satellite datasets specifically for these exact disk-like polarization patterns.
And what did the Bayesian analysis reveal?
The results were tantalizing, but excruciatingly, they were not definitive.
Yes, of course.
The team developed an algorithm that was incredibly strict, specifically designed to punish the multiverse model if it tried to overfit the data, ensuring they wouldn't be fooled by random cosmic noise. When they scanned the Eridanus region, their math revealed something astonishing. The bubble collision model actually provides a statistically better mathematical fit for the structure of the cold spot than the null hypothesis of standard random Gaussian noise.
Wait a second. You're saying that a literal collision with a parallel universe fits the actual hard data better than our standard accepted model of cosmology.
According to their rigorous Bayesian evidence framework, yes. The cold spot exhibits a temperature profile and a mathematically circular boundary that is perfectly consistent with the expected bruise of a bubble collision. This fit remained incredibly strong even when they factored in the complex calculations of how billions of years of subsequent inflation would have stretched and distorted the collision signal over time.
If that is true, why isn't this the biggest story in human history? Why wasn't the headline "Multiverse Confirmed" plastered on every newspaper worldwide?
Because in the realm of theoretical physics, providing a better statistical fit is vastly different from providing the 5 sigma absolute, undeniable proof required to verify a discovery of this monumental magnitude. The harsh reality is that the polarization data collected by the Planck satellite, while groundbreaking, simply wasn't high enough resolution to definitively isolate those incredibly delicate, localized B-mode splatters.
Why not? Planck was our best machine.
Because measuring B-modes is agonizingly difficult. You are trying to measure a microscopic twist and a microscopic temperature variation, and you have to look through the entire dusty, noisy, magnetically chaotic disk of our own Milky Way galaxy to see it. The noise overwhelmed the signal. The researchers concluded that we had reached the absolute physical limit of what our current generation of microwave background satellites can see.
So we are completely stuck. We have the perfect suspect, a mathematically flawless motive, a geometric profile that matches the crime scene exactly. But the security camera footage is just a little too blurry, a little too grainy to make out the license plate of the alternate universe that hit us.
We were stuck. For nearly a decade, the investigation basically hit a wall, until right now. To finally crack this cold case, to peer through the noise and definitively prove whether it was a void, a smokescreen, or a multiverse collision, we needed a new kind of magnifying glass, one big enough to map the entire universe with unprecedented, staggering clarity. And humanity has just successfully deployed it. Enter the ultimate cosmic detective tool, the Euclid Space Telescope.
Euclid. This is the European Space Agency mission, right? It launched recently.
Yeah.
And it has been making huge waves in the astronomy community.
It launched in July of 2023 with significant instrumental and analytical contributions from NASA. And it is, without hyperbole, arguably the most powerful specialized tool ever constructed for mapping the dark universe.
Okay, let's break down Euclid. What makes it so special? I hear people compare it to Hubble or the James Webb Space Telescope, but it does something fundamentally different, doesn't it?
Fundamentally different. Telescopes like Hubble and James Webb are essentially cosmic microscopes. They are designed to stare incredibly deeply into tiny, microscopic pinholes of the night sky, gathering light for hours or days to see the faintest, farthest individual objects imaginable. Euclid is not a microscope. Euclid is a surveyor.
A surveyor? How much of the sky are we talking about here?
Let's look at the specs. Euclid features a 1.2-meter diameter mirror, which is relatively modest compared to Webb. But the magic is in the focal plane. It is equipped with a staggering 600-megapixel visible light camera paired with a near-infrared spectrometer. The optical design allows Euclid, in a single snapshot, to cover an area of the sky 240 times larger than Hubble can.
240 times larger in one single picture.
Exactly. It trades infinite depth for unmatched breadth and precision. The mission is designed to systematically sweep the sky. By the end of its planned 6-year operational window, Euclid will have meticulously observed, mapped, and cataloged 1.5 billion distinct galaxies across roughly 1/3 of the entire celestial sphere.
1.5 billion galaxies. That scale is paralyzing. That is a comprehensive 3D map of the universe on a scale that is genuinely hard to wrap your mind around.
And the astronomical community isn't just waiting around for 6 years. We are already getting a profound taste of what this machine can do. Let's examine the Euclid Quick Data Release, known as Q1, which provided data dumps in March and November of 2025. This wasn't just a handful of pretty press release pictures. The consortium focused Euclid on a tiny fraction of the sky, about 0.1% of the celestial sphere, an area known as the Deep Field South.
0.1%, a tiny sliver. What did they find in 1 week of looking at a tiny sliver?
In just 1 week of observation, in that tiny sliver, Euclid clearly spotted and cataloged 26 million galaxies.
26 million galaxies in a week.
Some of which are situated 10.5 billion light years away, meaning we are seeing them as they were in the deep infancy of the universe. But the crucial part is that Euclid isn't merely counting glowing dots, it is actively classifying them. The Q1 data release highlighted a fascinating analytical framework the consortium calls the morphological tuning fork.
A tuning fork. How does a musical instrument relate to galaxy classification?
It is a visual analogy initially devised by Edwin Hubble, used to map the evolutionary paths of galaxies. Galaxies come in an incredibly diverse array of shapes and sizes: tightly wound spirals, massive featureless ellipticals, chaotic irregulars. The tuning fork is a system for categorizing these morphologies, which helps astrophysicists understand how galaxies physically evolve, merge, and change shape over billions of years of cosmic collisions and gravitational interactions.
But wait, if Euclid is capturing high-resolution images of 26 million galaxies in a week, human astronomers can't possibly sit there and categorize them on a tuning fork one by one. There aren't enough graduate students in the world to do that.
There absolutely aren't, and that is why Euclid represents a revolution not just in optics, but in data science. The Euclid Consortium relies heavily on advanced, bespoke AI deep learning algorithms. A prime example is an algorithm named Artemide.
Artemide. That sounds suitably mythical for a space mission. What does Artemide actually do?
It is an incredibly powerful neural network. Artemide is designed to automatically sift through the petabytes of Euclid imagery and instantaneously detect complex, subtle features that human eyes might miss. It can identify giant gravitational arcs, map complex dark matter mass distributions, and crucially, it is helping scientists uncover thousands of incredibly faint, diffuse objects known as dwarf galaxies.
Why are dwarf galaxies important? Don't we care more about the massive superclusters?
Dwarf galaxies were previously too dim and diffuse for standard surveys to reliably detect. But cosmologists theorize that these tiny, faint galaxies are the fundamental building blocks of the universe. They are the seeds that merged to form the giant galaxies we see today. Euclid, powered by AI like Artemide, is finding them everywhere, effectively rewriting our foundational understanding of dark matter halos and galaxy formation.
Okay, I am thoroughly convinced that Euclid is an absolute technological powerhouse.
Yeah.
It is finding millions of galaxies, employing AI to map the invisible building blocks of the cosmos, and surveying a third of the sky. But I have to bring us back to the crime scene.
Of course.
How does cataloging 1.5 billion galaxies actually solve the mystery of the CMB cold spot? We're looking for a subtle temperature bruise on the ancient microwave background, not a massive census of modern galaxies. How do these connect?
They connect beautifully through Euclid's primary scientific methodology, its dual probe approach. Remember earlier when we discussed how the Dark Energy Survey attempted to map the invisible dark matter of the Eridanus Supervoid using weak gravitational lensing?
Right. The DES mapped the toothpick-like distortions of background galaxies and determined that the supervoid was 30% too shallow to explain the cold spot via the ISW effect.
Exactly. But while the DES was groundbreaking, it had distinct limitations.
Yeah.
Its optical resolution was restricted by Earth's atmosphere, and it struggled to get highly accurate depth or redshift measurements for the background galaxies. Euclid was explicitly designed from the ground up to overcome those exact limitations. Euclid is going to perform the exact same survey the DES did, but from the pristine vacuum of space, with orders of magnitude more precision, depth, and clarity.
So Euclid is going to execute both techniques at once.
Precisely. The dual probe. Euclid simultaneously performs galaxy clustering analysis using its spectrometer to map exactly where the visible galaxies are in 3D space with pinpoint accuracy and weak gravitational lensing, using its 600 megapixel camera to measure the microscopic shape distortions of billions of background galaxies to map the invisible dark matter.
Oh, I see where this is going. Euclid is going to turn its dual probes directly onto the constellation Eridanus.
It is going to absolutely dissect it. Sometime between 2026 and 2031, as Euclid completes its southern sky survey, it will provide a definitive, undeniable, high-resolution 3D map of the total mass distribution, both visible and invisible, in the exact line of sight of the cold spot anomaly.
And here is the million-dollar question. What happens if Euclid confirms the old DES data? What if Euclid's flawless, indisputable mass map proves, without a shadow of a doubt, that the Eridanus Supervoid really is too shallow?
The implications are monumental. If Euclid definitively confirms that the gravitational void lacks the mass required to account for the temperature drop, it permanently and decisively rules out the integrated Sachs-Wolfe effect. It completely eliminates the standard lambda CDM physics explanation for the anomaly.
And if standard physics is mathematically eliminated, it aggressively, irreversibly tilts the balance of evidence toward the exotic.
It does. If the void is proven innocent, the multiverse bubble collision theory immediately becomes the most mathematically sound, logically consistent explanation remaining on the board. It perfectly explains a 150 micro-Kelvin drop. It perfectly explains a 5-degree circular geometry. It perfectly explains the SO21 mathematical symmetry breaking. Euclid's map of a dark matter void isn't just a catalog of missing mass, it is the final definitive verdict on whether our universe is alone.
We are literally standing on the precipice of a scientific paradigm shift. The data that is actively beaming down to Earth from that telescope right now over the next few years might completely redefine our concept of reality. It could elevate the multiverse from a fun sci-fi concept to a proven empirical fact. It could prove that our entire observable universe is just one tiny, expanding soap bubble in an infinite, eternally boiling pot of distinct realities.
It is a profound historic moment in the timeline of human science. We have successfully transitioned from philosophical speculation to testable, observable, hard data. The resolution of the cold spot anomaly has elevated itself from a statistical curiosity to one of the primary driving objectives of modern observational cosmology.
This has been an absolutely unbelievable journey. Let's take a breath and recap exactly what we have unpacked today. The CMB cold spot began as this weird, statistically annoying data blip on a satellite map, a dark thumbprint on the cosmic baby picture. Then, it evolved into a massive astronomical hunt for the largest empty spaces in the universe, leading us to the staggering discovery of the 1.8 billion light-year-wide Eridanus Supervoid.
But the void's gravitational alibi completely fell apart under the rigorous scrutiny of weak gravitational lensing and dark matter mapping.
Right, and with the giant void failing to provide the energy drain, and foreground smoke screens and cosmic textures proving either too geometrically messy or too untestable, we arrived at the most radical, breathtaking idea of all, that the cold spot is a physical, measurable bruise resulting from a violent collision with a parallel universe during the very first fraction of a second of time. And now, the Euclid Space Telescope is acting as our ultimate cosmic detective, gathering the final high-resolution pieces of evidence to either prove the void guilty once and for all, or throw open the door to the multiverse.
It is a profound testament to human curiosity and our relentless drive to understand our place in the cosmos. We saw a microscopic shadow hidden in the background static of the universe, and we marshaled the resources of multiple nations to build a billion-dollar space telescope specifically to find out what cast it.
And, as we prepare to close this cosmic case file, I can't help but linger on the idea of that bruise. If the multiverse collision theory proves to be correct, if our reality was genuinely rear-ended by another expanding bubble universe 13.8 billion years ago, consider this. What if that violent collision didn't just leave a temperature dent?
That is an intriguing line of thought. What exactly are you proposing?
Well, think about the mechanics of a real car crash. It is never perfectly clean. Paint transfers from one bumper to the other. Glass shatters. Physical debris from one car ends up inside the other. If the absolute physical boundary between our universe and a completely parallel universe was violently breached, even for a microsecond of cosmic time, what if the distinct laws of physics from that alternate bubble leaked into ours? What if exotic fundamental particles, governed by entirely different constants of nature, spilled over the boundary at the exact point of impact? Is it possible that hidden deep inside the Eridanus cold spot, waiting patiently to be discovered by the sensors of telescopes like Euclid, are physical, tangible fragments of an entirely different reality?
A literal cosmic paint transfer. That is a chilling and incredibly motivating scientific thought. If that hypothesis holds true, the cold spot isn't merely a bruise on the map, it is a doorway. A physical intersection where the rules of our universe no longer strictly apply.
It changes how we view absolutely everything. We started this deep dive by talking about how we fundamentally expect the universe to be orderly, clean. We expect it to look like a perfectly developed X-ray, showing a clean, understandable break on a bone. But we zoomed our satellites into the cosmic microwave background. We found that impossibly dark thumbprint hidden in the static, and we realized the X-ray is actually incredibly murky. The diagnostic landscape of the cosmos is muddy, chaotic, and full of shadows. And hidden deep within that mud might be the ultimate proof that we are not alone in the multiverse.
It is often said in physics that the muddy waters, the anomalies that refuse to fit the standard model, are exactly where the most profound and revolutionary discoveries are waiting to be made.
Incredibly well said. To you, the listener, thank you for tuning into this investigation. We hope you enjoyed diving into the deepest, coldest end of the cosmos with us today.
It has been an absolute pleasure to break down this complex evidence with you.
If you have any topics you want covered, any other unexplained cosmic anomalies, bizarre theoretical physics theories, or deep space mysteries you want us to investigate, make sure to tell us in the comments section. And of course, remind yourself to like and subscribe so you never miss a case file. Until next time, keep looking up and keep questioning the static.